particularly for gain bandwidth product, power dissipations, and stability is one major issue. We have done most of the analysis and also evaluated last time from the given data for a phase margin of 60 that CC should be related to C2, and we said that C2 is essentially encompasses the load capacitance and total load given to us is 10 puff. So the minimum value of CC which you can use is 2.2 puff, or it can be greater than 2.2 puff. Okay. So based on this we continue now. So if I have a choice of making CC, I can either choose 2.5, 3, 3.5 or even 2.2 itself, because that satisfies the condition of A. As I kept saying you earlier, larger the CC value I choose, better stability I will get, but then there is a problem of bandwidth. So I do not want to go too far from 2.2, at the same time I do not want to be very close to 2.2 either. Okay. So there are two possibilities I looked into, but maybe finally I decided I will choose one, either I choose 3 puff or 2.5 puff. So the further calculations were performed with 2.5 puff as CC. You can choose 3 and do same analysis again, or you can choose 3.2 and start doing everything. Okay. The values will keep on changing, the method may not. The only problem you must remember, any value I choose here will have implication of all W by L's and also the gain, and at that time you should see that gain should not be below 4000. So the issues are little tricky. So I believe that if you close to 2.2 you choose, things will happen, okay, because all this phase margin we have taken care of AB 4000 or something. So someday this value is good enough in my opinion, but this my opinion does not count, we should check it if necessary. So we know the slew rate is given to us is dV0 by dt greater than 10 volt per microsecond, and since last time I said the current which CC can receive is the maximum IDS 5. So based on this I have two possibilities. If I choose CC of 3 puff, this will be 30 microamps. If I choose 2.5 puff, this will be 25 microamps. So I am going to use IDS 5, or what is our ISS for DFAM, as 25 microamps. Okay. Is that okay? So choice of ISS, or what we now call IDS 5, is now chosen from choice of CC. So it will be different if you have a different CC. For example 3 it shows 30, 2.4 is 25. So it depends, it is proportional. So 10, so you can even choose higher than this, because you are asking higher than dV0 by dt, this 10 volt, but I am choosing 10. Okay. Why these numbers are given? So that let us say in the first round you do not meet specs you are looking for, so you come back and replay right from here. Okay. You say loop, come back and redo again. Okay, okay, so since I met the specs I am not going to do second time, but in case I would not have, probably I would have to do second time. So an individual arm of a DFAM, the IDS1 and IDS2 will be the half of this current, which is 12.5 microamps. So why these values are needed? Because GNs are calculated for these currents. Okay. So we also please remember that whenever I write VGS, I will be leaving 1 by lambda VDS term, lambda being smaller, and then I can always write VGS is equal to VT plus under root of 2 IDS upon beta dash W by L. Why this relation? Because if I know this, or I know something here, I am able to hit W by L through this relation. So one way of reaching W by L is this expression. Okay. So I like to use this expression once a while when I think I have other things known, so I may evaluate W by L for given transistor. And in this case obviously the over voltage or excess voltage is under root 2 IDS upon beta dash W by L. The third parameter given to us, third or fourth whatever number, is input common mode range. It is not really evaluation, from ICMR evaluation I should say. We have been given Vn minimum and Vn maximum. Please remember this word minimum and maximum are slightly, what I would say, they are not very correct. what I essentially means, the min word is taken from VSS and max word is taken from VDD, okay, whenever we calculate. But the actual value, this Vn min is the max value of that which is required, and this max should be the minimum what I want. Is that clear to you? So anything greater than 2 is fair enough, anything less than this also is good enough because swing is larger, fair enough. So please, this slight statement making is worrisome. So please, what I am saying, the value given to us is this is the minimum value of maximum which is 2 volts. So if I get 2.2 volt, I am fair enough. This is the at least I should have minus, so if I am below that I am still fair enough, I have larger swings. Is that clear? So this max min words are not really the actual max, they are taken, max word was given from calculation from the uppermost values, VDD value down and VSS value up. So this confusion should not happen that then you see you are not meeting specs, actually you are improving the specs. What is common mode ranges we are saying? We are trying to say that in this input swing the transistor remains in saturations. Is that clear? That is the range I have given you. So that is, if at even lower value it will be still be, if you go below VGS minus VT may not be smaller than or equal to VDS, then it will come out of saturation. So these are the values, so something going beyond is fair enough. It still, if I increase VDS fair enough, now how does it hurt me? Is that clear? So these values are essentially taken as min max, but actually they are max mins. So there is some catchword which I use, so I thought maybe in the end I may show you something different value, you say oh it hasn't met, in fact it might have done better than what was expected from me. So from this Vn min, if you see the figure, I may have to check the figure, I should keep it separate now so that every now and then I need that. We have done this expression earlier in when we divide those expressions. You can see from here the Vin essentially is, if I calculate from here, it is VSS plus VD sat 5, this voltage plus this voltage plus VGS of 1. Is that clear? To reach this point, I start from here, this voltage plus this voltage plus this voltage is Vin. Is that clear? So Vn min is essentially VSS plus VD sat plus VGS1. So and this value has been given to us is minus 1.125. You can see that 1 was added by me because when I did some calculations 1.5 I went out of the way because device came out of saturation. So I suddenly came out of, I say okay I put 1 extra there. Okay, so this expression and VGS1 can be written as VT1 plus under root of 2 IDS1 upon beta dash W by L1. Is that clear? Just now I wrote VGS expression, so I reuse that expression in writing V minimum. I may not use immediately this value which I am saying, but this is the expressions I am going to tell you. Okay, this I have finished. We also see Vn max. Max is taken from where? From the VDD side. So you come from here, you come here, then you come here, then you come here and then you come here. Is that clear? I repeat, you come from here, then you come here, then you come here, then you come here. Okay. So this is the Vn max which is the minimum value I want really, so that the device remains in saturation. Now if this function I repeat, so it will be VDD minus VT3 or VTP3 you should write if you wish, so that it is a p channel device minus, this is VGS3 I am writing. What is this? VGS3, okay, minus VDS sat for 1 plus, please remember VDS sat, please just, this is VDS sat plus VGS1. Is that clear? So VDS sat 1 plus VGS1 is given to be as 2 volt. Okay. So if I write 2 is equal to VDD minus VTP3 and this is n channel device, so please write VTN1. So and what is VGS1 minus VT? So we actually rewrite in that expression, so I get 2 is equal to VDD minus VTP3 minus this number but this essentially is VGS minus VT is VDS, okay. So that value I substitute as VTN1. I keep doing this, and finally from this, because I now know this, I know this, I know this. Now the only catch, I said that last time I did say that here I have used it 0.7 as the typical value of VTs, okay. And I said you that normally in max min values you should choose the worst cases or higher ones, so that max min values of those you should choose, which will give you that bar better than the normal. With this calculation I figured it out, W by L3 is just 2, okay, which essentially is what is the problem. If W by L of P channel device is smaller, the resistance is higher, so nothing wrong, but there the resistance is 1 upon GM3, which may not be then higher, lower actually. I want that to be higher. So I feel this 2 is slightly smaller value. So I did some tricks, you write down this, yes. Yes. Actually if you see that signs have been taken, this is 0.7 minus, no, this, that in writing we have already taken care of the sign, okay. VGS minus VT, so VGS has to be negative and VT has to be negative, then only it's always magnitude subtraction, because you cannot exceed the value given to the supply, okay. So using this, these are standard expressions. How much W by L I got for the transistor 3 is 2. We also have said that in all our designs M1 is same as M2 by size as well as VT, and M3 is same as M4 by both VT as well as sizes. So once I know W by L3, I as well know W by L4. So okay, in my opinion, since I chose the typical values of VT, I got into a small value of the, have you written down? I keep saying these are only trivials, just write this expression and maybe this, which and this is also sometimes rounded by me, so check it, because this is, I always hand calculate at times, not using calculators, okay. Is it okay? So if I use now VTP max as minus 0.85, VTP min is 0.55, that is I say bar of 0.15 is what I expect max min values to shift from the typical. Same way VT min is 0.5 and this is 0.85. So now if I say to get the value of Vn max, that has to be 2 volt, so I must subtract highest value of VTP, because then it should satisfy 2, okay. Then I should also satisfy the lowest value of VTN, because then it will be the worst case and therefore it will still should satisfy my 2 requirements. If I now substitute with this, I can recalculate W by L3 and it turns out to be 12.5, which is 12, okay. So just think of it, if there is a bar on VT, the W by L's can change by 5 to 6 times. This is an issue which I wanted to bring to your notice, that for me as a calculation I may say 2 is good enough, what's that big about it, but in real life the value may change as much as 5 to 6 times if your VT bars are such high values. Is that clear? So this, the designer should keep in mind that there will be a max min values always associated with the data given to you. Even they will specify 0.7 plus minus, okay, 0.15, okay. So they will specify that delta, and therefore right now I have used it same VT and same delta VT, but for P channel and N channel VT will be different and their deltas will also be different. So maybe you will have to do little more calculations correctly for the real life situation. For simplicity I have made equal everywhere, so that at least I get the numbers of my kind of numbers I am looking for. Okay, coming back to your Vn, what is the Vn max value you can see from here? From here if I want to reach Vn, one method is VGS3 plus drop across M1 VDS1 plus VGS1. Now if this value has to be say minimum maximum, for the worst case whatever I subtract that still should reach 2, that is the value given to me. So what do I say? Okay, so I will VGS1 I know is VT plus under 2 under root 2 current flowing through this. So I choose the maximum of VTP because that is the worst case available to me. When I calculate this drop is nothing but VGS minus VT, okay. So I actually now see to it that that drop is the maximum available to you. So I also accordingly put VTN so that because it will be subtracted out of this. Please remember VGS minus VT is VDS. So if I have to subtract out of it, I should choose minimum value of VT so that that is the highest drop across which it will come, so that still it will satisfy your 2 volt requirement. This is what I say vein minimum or maximum. But what does that mean? If something is lower than this, fair enough. Higher than this is fair enough, because these values are chosen worst cases. In fact, they will not be that bad. So this value will actually exceed 2 volt, but that is nothing wrong with us because devices are saturated even with these values. Is that clear? So anything beyond is still satisfiable. Is that clear? So the value we choose is called worst case situations. If that satisfies the saturation condition, then the other conditions are always going to satisfy. So we say, okay, we are well within our limits to actually see transistor remains in. What is our worry in all this? No transistor should come out of saturation. If this is the case, that is VDS must be equal to VGS minus VT or greater than VGS minus VT. As long as that condition I satisfy, I am always, so age is equal. So if that is satisfied there, anything higher VDS higher will be better. No? So I am safer when I say I take the worst cases, and then I say, okay, if it does not reach that, fine, thank you. Okay. That is the way we actually assume the values. Fine, because I am asking more swings. See, my worries are that how much gain I am allowed in. So larger input swing is better, and with that also devices define works, fantastic.
So I am asking if we have calculated 2 volts.
2 volts, if it becomes 2.2 volts, I am fair enough.
Gain is 2.2, this will work.
It will still work. How much, because that will still try to satisfy, as long as this condition is satisfied, I am least bothered about it. Saturation condition should not be actually defeated by me. That is, that minus value become plus. So gain min cannot be plus, it should be minus as such, okay, because the other end of the VID. What is we are looking for? Minus VID by 2 to plus VID 2, in this range device remains in saturation. I am trying to see if it does not go to minus side, it remains positive, then I do not have a swing. Is that clear? So with the minus 1.5 if I put, I find I went the other way, subtraction. So I said, okay, I will reduce that value, okay, so that still remains negative value, okay. You do calculations, I didn't bring those, but I did, and therefore I removed them actually, okay. Okay, so idea now is that I got W by L3 equal to W by L4 equal to 12. You can also, for the sake of brevity, you can say 2, it's okay, I mean nothing wrong, if you put it and everything else is satisfied, I have no objection of using 2, better if it is 2. Why? Because it will reduce capacitances, it will reduce also, it will increase resistances, so everything is fine, area will reduce. So I should not really boost W, okay. But my worries are that I may lose something else, and because I know typically it is around 10, so I thought, okay, I will see that what is the worst case situation I use and I will increase it. That is the trick. This you will not know because you have not seen actual chip. So because we have seen it, we know, okay, at least boost it little bit. And how do I boost it? I figure out this is the easiest way of looking at it, and it will be higher than 2 anyway. Okay. Okay, so once I have declared, so how many things I have now calculated? I have calculated W by L1 and W by L2, W by L3 and W by L4. So different के sizes are now fixed by me. Okay. Sorry, we have not yet reached 1. We will calculate from some GM1 requirements which will come from the other area, we will calculate, I am sorry, only we have calculated 3 and 4, okay, you are right, very good. Now as last time I said, before we proceed further, our assumption in stability was that the pole 0 at C, because of C3 in the DFAM, does not contribute to any stability issue, because these poles and zeros are far away from the last zero also, okay, which you assume Z1, even it is higher than that, and if that happens I say it is so far away, and fortunately both are on the left half plane, so actually it is not going to affect you in any sense as far as you are this, but this statement cannot be taken on a face value. So I did evaluate and check it whether those values are available. In real life, if you don't calculate 99.9, nothing goes wrong, but for the brevity I must say I will calculate. So if this is your DFAM, this is your equivalent circuit, okay, this is your input, then C3 is the capacitance, GO1, GO1, GO3. Why this GM3? Because this is diode connected, so GM3, and this is my VGS. On the other side from this arm, GM2 Vin plus GM3 Vin. Now this current which I am showing is the current flowing in this is actually getting mirrored. Is that correct? It is getting mirrored. So that mirror currents are shown here. So this GM3 Vin, GO2, GO4 in parallel. And if I solve this circuit, which you should be able to, how do I solve? These are resistances, these are currents which I calculate. Please solve this. This is a standard DFAM theory. I don't ask me to redo the DFAM again. Okay. So I calculated the current gain, transfer gain for this DFAM, which is V0s by Vns, and it turns out to be, why I use GOs now suddenly, because I say 1 upon RO becomes difficult. So if I write G's, I just add G's. So sometimes I do G's, sometimes I do R's. You can make your choices as much. This is if you know, myself and Professor Sharma have been teaching these courses many industries. This G business is with him. He always liked to write GVs is I. So that is why sometimes when I am teaching with him, I also follow his way. So these expressions were picked up from my other old slides. So okay, so I got this big expression GM1 upon 2 GO2 GO4 GM3 plus GO1 plus GO3 upon GM3 GO1 GO3 plus SC3, that is the impedance due to this. Solve Kirchhoff law and get these expressions plus 1. Now I can say GM3 is much larger than GO1 and GO3, and then we start doing some interesting calculations. So I get minus GM1 upon this. This can be expressed as 2 GM3 plus this 1 है ना, ये GM3 plus 1 में गया, so that becomes 2 GM3 plus SC3 upon GM3 plus SC3 when we say GMs are larger than GOs. Okay. Further, if we keep doing the same this, we can say the third pole, you can say from here, third pole is because of this, which is minus GM3 by C3. This 0 means this is DC gain, this is pole, this is 0. So P3 is minus GM3 by C3, which is GM3 upon 2 CGS3. Why 2 CGS? At that point CGS of 4 and CGS of 3 are in parallel, so I just made 2 CGS. Now what is Z3? 2 GM3 is SC3 is coming, so it gets 2 GM3 upon 2 CGS3, which is GM3 by CGS3. So which is higher? The 0 is still at higher frequency than the pole 3. ये 2 है ना, ये ज़्यादा है यानी कम है, ये कम है यानी वो ज़्यादा है, ऐसा है. Denominator is smaller, so the value is larger. Denominator is higher, means value is smaller. Is that clear? Is that okay? Therefore Z3 is twice of P3, that means Z is still ahead of P3, but both are of which sign? Minus, left half plane, fantastic, no issues, okay. They are far away from P2, they are far away from GBW, so we say okay, if the values which I calculate for this comes out to be in gigahertz, I say thank you very much, okay. So now to do this, have you everyone noted down? As I said, this I am only showing you for the sake of this, you should not say why I leave that. So I actually taken a data and substituted this. What is typical CGS should be 2/3 COX, okay. Is in saturation, typical value which CGS can be given is, of course there is a overlap capacitance, so you may add something additionally, but typical value as this we can choose as 2/3 COX. but that COX is per unit area. So what is the area of this transistor? W3 into L3. What is the technology I am using? 0.8 micron. So I choose lengths as 0.8. It is not compulsion. I am choosing it. You can choose some other values of length and still do everything. Okay. COX from the data sheet is 2.47 femtofarad per micron square. 2.47 10 to the power minus 15 femtofarad, or not 15 then, 2.47 femtofarad per microns square is the value of COX. I multiply it by 12 micron by 0.8 microns, W3 by L3 into L3. This is in micron square now. Is that clear? So I don't have to write 10 to the power something, because this itself is now taken in micron square. So I just multiply it. So I get the capacitance CGS as 15.6 femtofarad. Okay. Is that clear? CGS. I want to calculate GM3 because the pole and zeros are related to GM3. So I substitute GM3 is 2 beta P dash W3 by L3 IDS3. What is IDS3? Half of IDS5, which is 12.5 microamps. So if I substitute beta P as 50 into 10 to the power minus 6, IDS3 is 12.5 into 10 to the power minus 6, W by L3 is 12, and solve, I get 12.24 into 10 to the power minus 5 Siemens.
This W by L is 12 or W is 12?
W, if L is 0.8, it cannot be 12.
So here we put W3 is 12, but W by L is coming 12.
Okay, so some small number will change. You are right. I am sorry. I probably assumed 1 and did that, but you just calculate from there. You are very good. No, so it doesn't matter. So that's why I say I am not changing. You are right, but he is right. For a 0.8 micron, W by L3, it will be more than 12. Okay, maybe 10 by 0.8. So around 13 point something. Okay, instead of 12. Okay. So if I got, so what is the pole now? GM3 by 2 CGS. So I got a pole of 3.9 gigahertz. If I add CGS more, it may slightly go down, because then it will be slow. It may come to little 1.8 gigahertz or 2 gigahertz. Even with additional capacitance if I put, I am still in the range of gigahertz. Okay. Please remember, this is not gigahertz, this is in radians per second. So आपको उसको frequency ले 2 pi से divide करना चाहिए. So F3 जो है pole के लिए FP3 is around 625 megahertz, where FZ3 is 1.25 megahertz gigahertz. How much is your gain bandwidth given to you? 6 megahertz. 600. Z1 कहाँ रखा है? 10 times रखा गया था GBW का, 60 पे रखा गया है. ये उससे भी 10 times आगे जा रहा है, ये उससे भी डबल और आगे जा रहा है. So we can say that C3, the poles and zeros due to C3 for the case we are solving is of inconsequence as far as the stability issue goes. Otherwise you may have to even take transfer function which is third order, and then equations will become even more complicated. Is that clear? In our calculation we thought C3 doesn't exist, so I thought why I did not take it, so I wish to verify myself. Okay, I said okay, I said you, but maybe for other case, because I have data which is from other technology 5 micron. So I said let me check with the data available for 0.8, and then I figured out that even with this I am far away from GBW, and therefore P2 also. So anywhere I am not close by. Okay, so I say do not worry too much about C3s. So that is why in all analysis in many books they won't even show this C3. Okay. The reason probably is for a given technology this will normally not affect any of your stability issues, and therefore they do not consider, but for our sake I want to now clarify that why designers sometimes do not tell you but use it anyway. So this is what they use it, they know by experience this will be too far away, forget it. Okay, forget it. The reason why, because CGS is in what value? Femto, others are in picos. So that number ratio itself is telling you that you will be far away from this situation. CJS is in the order of femtofarads. Okay, this is the reason why it will always be far away from it. Okay, is that okay to everyone? Okay, so now once we said that okay, I am not going to utilize this transfer functions for 3, though I did this evaluation for the heck of it. Now I said I will like to calculate W by L1, so here is the calculations. We know gain bandwidth product in radians, not if it is in hertz multiplied by 2 pi, so it is GM1 by Cc, or which is same as GM2 by Cc, and that is given to you as 2 pi into 6 megahertz. That just writing 6 megahertz is not correct, that is not the frequency, it should be written, that is in actually radians. Okay, so you should write in radian per second, you should always multiply it by 2 pi to make it hertz. So if this is the value which is given, then I calculate GM1, GM2 is 94.2 microsiemens, S is not second, microsiemens. So what can I calculate? IDS1 is known, beta n dash is known, so all that is missing is W by L. Okay, so I substitute these values here, okay, and I get a value of W by L equal 1 is equal to W by L2, which is equal to only 3, which is correct. The reason why the lower transistors are always, because of the capacity effect they hold, that should be smaller than the loads, is that correct? That is how the large current, this is a P channel device, this is N channel device. So match is to be there, so N channel device should be smaller than P channel device for same currents to flow through. Okay, so this value which I got is, now you can see the value I got is 3.23. In our layout editors there is nothing 3.23, it is only integers are allowed. Okay, so never use very random numbers. Okay, always try to go to the nearest integer, and in most cases I did not do it, you should actually make it in binary numbers, 248 kinds. In layouts the simplest way of doing designs are 248, but the problem is if I use 10 I have to re-evaluate for all of them and check whether I am right, so I am not doing it, so I am keeping 3, but in real life simulation you do not mind, isn't it, so you will put that value at higher value elsewhere and check if it works out fine. Okay, why I am not doing it, I am telling you as such, these all values are never actually used by us in designs, okay, because the layout editor does not give accuracy of such second decimals. Okay, so we normally do not play too much, nearest value to that we use, and we also check right now, of course I do not know whether this is worst case, we always see to it that the worst case is chosen, so that with this also if it is satisfied, if I choose higher value it will always satisfy. This way I do not know whether this is the worst situation, but I just rounded to 3. What should be the what values I got now? W by L1, W by L2, W by L3, W by L4. So DFAM के main चारों transistor I know now their values. So which is the last value in this DFAM? The 5, which is your source. Okay, as other things to that. So that the next calculation should be now performed for W by L 5. Is that clear? All my procedures are based on individual, how to reach each value of W by L. Yes.
WL1 is less than 1.
Length बढ़ा देते हैं. If you increase the length, then lambda change. Length is allowed to be changed, it is not, but again it should be integers. Let us say it is 0.8, the next value will be 1.6.
So doing all calculations, just change the length.
No, but lambdas will vary. At different length lambdas are different. So you will have to, from the spice you will have to find which is lambda.
Suppose I got WL1 is less than 1.
I agree with you. I choose 12, let us say, for that. Okay, for that 12 value you must get your R0 correctly for the lambda different now. Is that correct? If R0 changes, all gains will change, all poles will shift. So there is an issue which is not just by putting 2. Okay, you can always use it. Of course this value will never come less than 1. Okay, the least you will get is 1. Okay, but in case it comes, this is doable. Okay, Is that okay? So the next value I am interested in this, so I use now Wien minimum value, VD sat, this is 1.125, I rewrite that expression. So anyway, so I got VD sat 5 from this calculations, IDS 1 I know, beta n dash I know, W by L1 I know, this I know, this I know, this I know. So I calculated VD sat 5 as 0.246. ये माइनस ऑफ माइनस इज 2.5 प्लस, सो ये बाकी सब वो इशू वही हो रहा था, ये उल्टा हो रहा था. यू मस्ट हैव ऑब्जर्व देयर, यू नो, वहाँ बीच में ऐसा एक लाइन लगा के 1.12 कर दिया मैंने उसको, 1.5 से वो बहुत बाहर गया एकदम. यू जस्ट लुक एट इट, इफ आई पुट 1.5, सो कभी कभी डेटा जब रैंडमली चूज करते हैं ना तो ये प्रॉब्लम हो सकता है. You got the point? What could I, if I put 1.5 here, this would have become negative. Okay, so I just उसमें थोड़ा कम कर दिया मैंने, so that it becomes at least positive. This is taken other side ना. Okay, so once I know VD sat 5, so what can I calculate? What is VD sat 5? Is equal to, by current I can calculate IDS sat is, IDS 5 is beta n dash by 2 W by L5 into VD sat square, VGS minus VT. So I did IDS 5 expression likha, and from there I evaluated W by L5, okay, which is 7.58, which is rounded to 8. Why I am saying I am not worried too much, because these are the specs you will start with your design and verify. Is that clear? But if you have no such values, you may choose 16, you may choose 4. So where do you initial values of W bias be chosen? This gives you very good guess for that. Okay. So in 2 or 3 turns of spice, you will actually get the all specs correct. 5 ho gaye. What is the next one now? The gain stage. Okay. You know, I always say as if DFAM doesn't get, DFAM gives equal gains, but normally DFAM is not still gain stage. The next stage of amplifier is called gain stage. Okay, now if I say W by L6, I go back to see my phase margin relations. I figured out from there, if you check our earlier, GM6 by GM1 should be larger or equal to 10. I assume the equal value, GM6 10 GM. GM1 I have just calculated, okay. So GM6 is 942 microsiemens. From there what can I calculate? What is the next thing I am interested in? Because मेरे पास एक data है V out max का. What is V out max from your expression output per? VDD minus VD sat 6. Okay. Now I must now calculate VD sat 6. So if I know GM, I should be able to evaluate VD sat 6. To do this, I do little trick. I write IDS 6 expression, which is half beta p dash W by L. Instead of this, I write VGS 6 minus VT 6 square into this, differentiate. Okay. So I get GM6 equal to half cancels, 2 cancels. So beta p 6, 2 of this. So ये VGS minus VT, but that VGS minus VT is VD sat. So I got beta p into VD sat 6 as my GM6. Is that okay? So now I have W by L6 is essentially equal to GM6 by beta p dash 6 into VD sat 6. But VD sat 6 अभी मुझे नहीं पता है. Okay, that I will now calculate. Is that okay to all? From here I got a relationship between GM36. Okay madam, sorry, वो differentiate में 0 ही हो रहा है वैसे VG के साथ. Anyway, lambda term is small, so you can always start neglecting whenever this GM's calculation starts. Whenever GM calculation starts, so W by L6 is GM6 upon this. What is V out maximum we have given to you? VDD minus, please look at the figure, just a minute. VDD minus this is the VO, is that clear? So I say okay, VDD minus VD sat 6 is my V out max. So VD sat 6 is VDD minus V out max. So 2.5 minus 2, which is 0.5. Is that correct? if I know this, I already evaluated this, so what do I calculate? W by L 6. समझा? कहाँ से कहाँ ले गए? क्योंकि एक एक्सप्रेशन में वो नहीं दिख रहा था, तो और क्या डेटा दिया है वो वहां से मिल सकते हैं. That's the trick in design. Is it clear? Once I get VD sat 6, then I know V out max is VDD minus that. So I actually evaluate VD out max is given to me as 2 volt. So I get VD sat 6 as 0.5 volt. So W by L 6 is GM6 upon beta P dash VD sat 6. Substitute, this is 50 10 to the power minus 6, this is 942 10 to the power minus 6. So W by L 6 is 37.67. ये अभी अब जो मैं बता रहा हूँ, that's the most worrisome part in design. Okay, that's what I am going to tell you why this value I am not accepting. I said fine, W by L 6 if I calculate I get 40 value roughly, and for this the ID6 is 235 microamps. What is that maximum IDS5 I am flowing? 25 microamps. This is roughly 10 times I am pushing in the last transistor. Okay, size of W by L of 40, like a buffer ही लगा रहा हूँ मैं. That is not very much good because this seems to be excessive power consuming device. Okay, because आपको power का भी एक limit दिया हुआ है. So I said there is something I must have done wrong, or at least I am not getting the correct value which I should get. Okay, so I said okay, I have another way of calculating W by L. Let's check with that. Now you can come back to this circuit. Do you see this M4 M6 also forms a mirror? ये connection दिया हुआ है आपको. Actually क्या है, थोड़ा circuit बराबर नहीं है, but actually connection जो है, it is like this current, there is no everywhere gate, so this mirror is mirroring in this in the ratio of M6 to M4. I just let you. This VGS is equal to this VGS. Okay. This VGS minus VT is this VD sat, which is same as this VGS. If this VGS, this is very close to this value, this current will be mirrored in M6 by some ratio of size, M6 to M5. Okay, you try this is what we did. Okay, मैं मेरा expression भी है, वो देखो आप तुम. So IDS6 by IDS4 is ratio of sizes. However, that means, and that is the verification. What does that mean? VGS SG6 equal to VGS SG4. ये condition मांगा ना आपने. अब मैंने उसको इस condition के लिए equate किया इनको. GM6 निकाला, GM4 निकाला, इनको yes. So VSG6 is equal to VSG4. So I calculate GM6. I calculate GM4, the ratio of the two is W by L6 by W by L4. So as long as I prove you that these are equal, my assumption of GM6 by GM4 is same as W by L6 by W by L4. GM4 I can calculate. Why? Because I know this current, I know the size, so I calculate this as 12.24 10 to the power minus 5 microsiemens or 122 microsiemens. GM6 by GM4 is ratio of W by L6 by W by L this. This I know, this I know, this I know. Is it okay? Everyone written down? GM4 is 122 microsiemens. I got 0.4 microsiemens. So I get GM6 by GM4 into W by L4 is W by 6, which is now 92. How much was earlier? 40. Now I increase it to 90. Okay, that seems to be. But if I now calculate VD sat 6 for this, I get the value of 0.203. Then I calculate the ID sat 6 current for this, which I get how much value? 95 microamps. This is compared to 235, this is acceptable limits for me. Is that clear? So I chose my tricks. I say कुछ और तरीके से बनाऊं क्या मैं इसे. So I found that if I now choose larger size of W by L, I can get different VD sat value, and for which then the ID sat or ID6 will be 90 odd microamps. पहले कितना था? 235. पावर डाउन कितने से किया? एटलीस्ट 2.5 टाइम्स नीचे कर दिया मैंने उसको. Okay. because my worries are at the end power estimations. Okay. Though actually since the currents chosen by me are so small and the limit I put was too high, so I think anything is satisfiable there. 2.5 milliwatts is a huge power. All that we are going to get is less than a watt anyway, milliwatt, okay, with all calculations. So this 95.8 microamp is reasonable value from power thinking. So I say okay, start using W by L of, instead of 40, boost it to 90, okay. So that now at least our currents are now within my acceptable range. Also we can find from here how much is V out minimum you will get, can anyone tell? So 2.2 or something, so which is fair enough because we are expecting 2, so it is swing is more, so fair enough, okay. What is the next transistor left now? 7. Please remember I kept telling you earlier also, the current in is not decided by M5 but decided by M7. So this current is flowing here, this current is fixed by you, okay, for GM sized. So the ratio of this should be such that it sustains the current of flowing from M6. Is that point clear? I repeat, the current in this arm is not decided by this. This is the load transistor there, okay. This is the driver. Current is picked up from here, which actually goes down through M7. However, M5 and M7 are in mirror, okay. So for this current and for this current I will then make a size ratio, okay, so that this current flows through also M7. So it looks as if I am biasing to that, but actually I am not biasing randomly, same current I am not passing. I am biasing it correctly such that it flows that much current in M6. Is that point clear to you? I repeatedly saying don't push same current here, because in that case this current will be different. So come from M6, figure out what is the current you are expecting to get that W by L, for that W by L, use that current for M7 and then find the ratio of this to this. This current I know, this size I know, this current I know, so I know the size of M7. So M5 and M7 are in current mirror configuration, so I6 is I7 and also I6 I7. So I get W by L7 is 8 times IDS 6 upon IDS 5, 95.8 into this, so I get a value of 30.65, so nearest value is 30. Normally how much I should put? 32, but I am not sure whether it will change VD side how much, so I kept 30. Okay. Is it clear? M5, M7 are in mirrors, but M7 is now drawing 95 microamps current. M5 is only drawing 25 microamps current. So the ratio of M5 to M7 should be 30, so that it actually matches to plus into multiplied by value of W by L5, so it is 8, 8 into this ratio is roughly 30.65, which is 30. Now I verify that whether VD sat is okay, so I substitute this value of in IDS 7 and evaluate VD sat for that. That comes out to be 0.23. If I take it from VSS, it becomes minus 2.27. How much was expected? Minus 2. So I am not worse off, I am still better off. So with this new calculation for W by L6, I am actually improving my output swing. Remember, what is the best swing you should have? VSS to VDD. Any amplifier output, if it can swing from VSS to VDD, is the ideal situation. The minimum, if you can further go down towards VSS, still better. Okay. So nothing goes wrong if I go below minus 2, because we are actually expecting ideally full rail to rail, which probably may not happen because saturation. What does this condition is trying to say? Device is still in saturation. Even with this will still remain into saturation, so good enough, okay. And we are improving the lower margin of the V out, so that is larger swing gauge. There we increase beyond 2, here we reduce minus of that, so very good, Okay. So in some sense we are getting better swings than what we are actually asked to do. Is it okay? The next value, what is left now? Sizes we are done, except the biasing side. Okay. Now what we do is to calculate power. कितना पावर दिया मैक्सिमम, वही बोला बहुत ज़्यादा दे दिया मैंने, रैंडमली रख दिया 2.5 milliwatt. Okay, doesn't matter. What is the current flowing in this? How many arms? Please जरा इधर देखिए सर. सर वो लोकल लूप जरा इधर भी देख लीजिए. How much currents are flowing? One current in this arm, one current in this arm, and one current in this arm, and one current in this arm. Into VDD is the, so together I will call it, because I am going to put equal this value, so I say twice, okay, plus current due to I5 into VDD plus current in this into VDD, so that is the net power dissipation. Is that correct? Each arm current multiplied by VDD, sum all of them, that is the net power dissipations. So I said okay, I bias circuit plus I diff amp plus I gain stage into VDD minus VSS, because the swing is full to rail, so 5 volt. So I find out I bias circuit IDS 5 plus IDS 6 into VDD minus VS. I bias circuit is how much? I bias circuit is sum of this current plus sum of this current, 9 and 12, okay. So if I write that I12 plus IDS 9, and now I assume the mirror is 1 to 1. What do I assume? M1, M9 and M12 are mirror 1 to 1. What is the current I want to? So I said okay, I can choose any current. So I said since 5 is running 25, I will half it. Okay. उसका size 8 है, इनका 4 कर देता हूँ मैं. So I have chosen size 4 here, size 4 here, and how much current each is drawing? 12.5 microamps. So if I do that by mirroring this, as I said, these are my choice, you can choose any other value, because mirror doesn't matter, any two, you can start with 2, 1, that ratio will change. Is that clear to you? ये 12.5 है, इसके जगह और कोई लोगे तो W by शिफ्ट हो जाएंगे. So any values, I for the simplicity ये twice किया है, तो इसको 4 कर दिया मैंने, आधा कर दिया. So if I do this, W by L9 is same as W by L12 because I kept them that way. So each is drawing, each has size of 4 and each is drawing half of this current, which is 12.5. So the bias current total is 12.5 plus 12.5 into 5, which is 0.125 milliwatts. How much? 125 microwatts. So itne सब में इतनी power गई. Now we also want to find the R value bias के लिए. अभी तो R नहीं बताया ना. How do I find out? If I know VGS for this, which is same as VGS for this, then this value minus this voltage divided by 12.5 is R. Please remember, this voltage minus this voltage divided by R is 12.5. So I did this and have calculated resistance to be VGS minus VT is VD sat. So for this value I calculate VGS 12 as 0.946 volt. Is that okay? This is the 0.246 which I got saturation voltage plus 0.7 which is the VT. Here also you can choose the worst cases and figure out what should be the correct this. And for this I calculate, is that okay? VGS, please take it, 5, 9, 12 are in mirror, okay. Their VGS are same, their VDS also are same, okay. One of the VD sat 5 is known to me, so I can evaluate VD sat for this. Current I know, so I know this, I know this voltage. If I know this voltage minus VSS minus this voltage divided by R is the current 12.5. Okay, so ये expression निकाला, R is equal to VDD minus VSS minus VDS 12 into this, which gives me a value of 325 kilo ohms. Okay, to get the currents of 12.5 microamps, I need for this W by L of 4, I need a size of current resistor of 325 kilo ohms. बायस का कितना पावर बताया मैंने 0.125, अवेलेबल कितना था 2.5, तो डिफैम प्लस इसके लिए कितना अवेलेबल है 2.375 milliwatts is still available for me for the limit for डिफैम प्लस गेन स्टेज. बायस का हटा दिया ना. Now let's calculate the power for DFAM plus gain stage. How much is the current in DFAM? 25 microamps. How much is current in I6 or I7? 95.8 microamps. Multiplied by 5, you get this 0.6 milliwatt. Okay. उसमें यदि 0.125 जोड़ भी दिया जाए तो it is 0.725 milliwatts, which is 1/4 of what was given to us. So we are given W by S and currents I chose, I am well within the power dissipation limits. So what is the next game you can play? Increase currents, higher slew rate you can then gain, recalculate all values of W by S and see whether still remain in saturation but it satisfy conditions better. Is that correct? Because at the end of the day this may be sufficient because low power is one of the major criteria, so we are anyway achieving it. But let us say you suddenly say 20 volt per microsecond you want, then probably you may boost the current but recalculate everything again with this new IDS5 and do till you satisfy again your power and slew rate requirements. Keep doing as much as you wish, okay, and at the end you will find some better optimal. In some case you may increase to 40 volt per microsecond, that is very very high speed but relatively low power compared to what limits you are given. So it depends on the spec given to you, you may actually still play with IDS values, IDS5 values, and if you play that value then please remember every other W value will change, okay, and then you receive it. Sometime device में जैसे मैंने गलती से वो VOI max behind mix गलत लिख लिया, so then I find it became the other side. So verify that those limits are also then modified by you, okay, so you can get some value. What is the last thing left for me to evaluate? Gain. अभी तक gain नहीं निकाला ना, इतना OPAMP का सबसे पहले क्या बोलते हैं gain, वो सब निकाला पर gain नहीं निकाला, अभी gain निकाल लेते हैं. Is it okay? Which gain we are interested in? The mid band gain, that is the DC gain. ये एक्सप्रेशन कैसे निकाला मत पूछना, ये पहले दिन से निकाल रहे हैं, ओके. GM1 by this is a total 1 upon RO2, RO2 parallel RO4 is essentially by denominator GO2 plus GO4, okay. GM6 is GO6 plus GO7, so if I multiply it becomes, अच्छा ये बताइए 2 कहाँ से लाया मैंने, because current in each is IDS by 2, so मैं ऊपर कर दिया उसको. 2 और 4 में सेम करंट है, IDS 5 by 2, is that clear? 2 and 4 में सेम करंट है, IDS by 2, so उस 2 को मैंने ऊपर डाल दिया. वो इसलिए क्या कि then this currents you are, why I did all that, because this current is what is your specification currents, IDS 5, so उसको मैंने उसी फॉर्म में रख दिया. Now given to me is for N channel it is 0.04, for a P channel it is at length of equal to 1 micron. What is the length we have chosen? 0.8. So we believe that this is same this. So you are asking, you increase the length, this lambda may go down. Is that clear to you? Then you have to recalculate other things. So I know GM1, I know GM6, I know lambdas, I know IDS5, I know IDS6, so I substitute 2 into 94.2 into 942 into 10 to the power minus 6 into minus 6, so minus 12. This is 0.09, so this is, both are 0.09, so 0.09 square. This IDS is 25 microamps, IDS6 is 95.8 but just put 95 microamps, so AV0 comes out to be 9225 volt per volt. कितना gain आया? 9000. What was expected? 4000, which is far away. So now we are another game. Oh, I don't want really this big gain, okay, so I can release this, okay, so I release the currents or reduce the size. So So now there are parameters which you are in hand, keep playing, but every time you change something, फिर सब करो. There is no other way we can do this, but that's how what we do is we go on one calculation and submit it to SPICE and believe that it knows better than me and therefore accept whatever that they say. Okay, that's the way all of us actually believes. So is that clear? ये हो सकता है कभी कभी ये कम आ गया तो फिर तो करना ही, you have to do, because gain is one of the major parameters of OPAMP. Is that correct? So no compromise can be made if this goes below the specified value. Unfortunately, the way I did this simulation, which is what easiest to think in my some books, journals also have given this. This is not my original. Okay, I am not claiming it. I did it some many years ago, but it is not that it is my original. I am copying indirectly from somewhere. Okay, right now I am not saying it, but means I have done 8 times, so I know this. Please remember, this is the crucial factor we will have. Okay, what is the problem if I use this value, higher value? The bandwidth will go down. Okay, so some limit they say no, I want at least this much bandwidth, then I cannot play with this gain. So I say okay, थोड़ा नीचे करो तो बैंडविड्थ बढ़ेगा. ओके, क्योंकि गेन बैंडविड्थ दिया है ना आपको, सो आप गेन कम करोगे तो बैंडविड्थ बढ़ जाएगा. तो फिर वहां से एक लिमिट लेके आओ बैंडविड्थ से, फिर इसको रिसाइकल करो. ओके, दिस इज हाउ OPAMPs आर एक्चुअली गेट डिजाइन्ड. ओके, हाउ मेनी पेजेस आई स्पेंट यू डोंट नो, ऑलमोस्ट 42 and there are 4 more to show. Okay, so you can imagine the design is not very casual approach. Design requires lot much thinking and lot much evaluations and then hope for the best. Okay. And at the end of the day, hope for the best. Is that clear? If you could have calculated first, you could have solved much of his worries, but right now I did not know GM, I did not know 6, I did not know these G's that time, so I could not do it. Till I got all W by L's, I cannot evaluate these. When I evaluated, then I am already coming to an end size. And then I started looking for gain, then I was hoping कि वो नीचे ना चला जाए. कब कम हो सकता था यदि ये lambda values बढ़ा दें. Now you think of it, the issue which I am saying is the most crucial. Let's say lambdas are equal. Okay, so this is 2 lambda, this is 2 lambda, that is lambda square terms आ रही हैं. So any change in lambda square में वो गेन को हिट करता है. You got it? Is that okay? Any change in lambda 0.04 का 0.02 करते हो तो 4 times निकल जाएगा आपके हाथ से. ओके, तो ये 9000 जो है वो 2000 हो जाएगा. तो ये लैम्डा वैल्यूज जो है उतने कैजुअल मत लो. इज इट शुड बी क्लियर? इफ आई जस्ट half it, I may figure it out that I don't get the gain even. Okay, so therefore this evaluation of lambda from the SPICE file is a very crucial factor at every length. Okay, कैसे निकालते हैं? IDS VDS प्लॉट करिए, हर इसके लिए उसका स्लोप ढूंढिए और वो यूज करिए. Is that clear to you? So that is something which any designer must first do. These data has been chosen from a normal known value, so they came correct, but in case they are not, actually you must evaluate. Is that clear? Plot for given sizes of your various W by size के लिए IDS VDS कैरेक्ट उसको निकालो, उसका स्लोप कैलकुलेट करें और सबका एक लुकअप टेबल बनाओ. Okay, and then when it comes, pick up from there. Okay, so that is the actual design things go. Last but not the least part in this, before we finally go, and which I am not calculating right now, I am just showing you. This is also my old slide, I am just re-putting to you. One of the technique which we used in this design was splitting up the poles. What is the method I used? I put a mirror capacitance and compensated. So what did I compensate? The non-dominant pole was shifted far away by so much factor, whereas the dominant pole came closer towards the other side. Okay, and then I am worried whether my bandwidth is okay or not. The one other technique is that why not compensate the non-dominant pole itself. Okay, Since you have a 0, so if I instead of just capacitance I put in series this circuit figure, if I have, maybe I can show you something here. Instead of this I should use something like this. This is my R, this is my CC. Please remember this R is created by bias, something here called VA. No one is telling you it should be in saturation or non-saturation. What is the choice you have to do it? R from that. If R is required smaller, choose put such that it is in non-saturation. If R required is higher, go for saturation. Is that clear? So I don't want to specify what VA. From where this VA I can get? That bias circuit में वो डायोड्स लगाए रखे हमने, वो 2, 3, 4 रखना पड़ते हैं जब जो VAs लगने वाले हैं उसके हिसाब में उसका वोल्टेज निकाल लेते हैं. Once that voltage is known, you fix that voltage here, connect here, okay. Once you connect here, this R is known to me because the W by I calculate for this, okay. When that RC time constant is known, I have now new Z1 which is minus 1 upon RZCC minus CCGM6, which is negative on the left half plane. Please remember, if RZ is larger only then this will go to left half plane. Smaller the RZ, this may be dominant than this, and in that case it will become positive 0. So a right half plane 0 can be shifted to left half by increasing RZ value. Is that clear to you? Just look at the 0. If I want to make, this is the minus here anyway. If this is smaller, then this will become positive. So I am on the right half plane. If I start increasing this value RZ, is that clear? This is minus, then this is minus, so plus हो गया, right half में गया. If this is larger than this, the pole is 0 is on left half plane. So and then where value I should put that Z1 equal to the P2. So I will cancel that P2 once for all because P2 was necessary with this CC. So I say CC I don't want to increase too much. Is that clear? Now I say okay, if that split has to be, then why split was necessary? Because P1 P2 are very close. So stability phi was an issue for me. So I say उसको ही निकाल देता हूँ ना मैं बाहर. If I have to remove that pole without splitting or small splitting, then I will be able to actually keep CC smaller. Is that clear to you? That is how I must remove the second pole. This is called nulling. This is called nulling. So bring a 0 exactly on the pole at that P2 value which you have. So P2 is given to you as minus GM6 by 6, and if I equate this by this formula here, I get RZ is equal to 1 upon GM6 CL plus CC. C2 है यहाँ पर, मेरे पुराने में यहाँ C2, नए इसमें C2 है. Load capacitance in my this is as I say old slide, so load लगा हुआ है. So RZ GM6 minus 1. So but I can now, I know GM6 where I evaluated, so this is the expression. So RZ can be realized once I get this RZ value, then using this expression, if it is in saturation or non-saturation, get the correct expression and evaluate RZ for that. That RZ value, for that W value evaluate, put that value such that Z1 is exactly at P2. Is that clear? Once you nullify the non-dominant pole, the only pole with you is P1, and that P3 is still away, so you are not caring. So only one single pole you have, which you can then think of what CC I should use, because so that it should not be too close to 0 axis. Okay, that is the trick. So RZ allows you to do that. Is that clear to you? And then your bandwidth essentially is not directly hurt by this method. So to improve your bandwidth, one way is to null the non-dominant pole and keep CC lower. Is that clear? So this method of nulling is very powerful. The only problem is, what is the only problem you get? All these values are varying with all kinds of variations. So getting this relationship is not very easy, that they is null. So some then still will occur, but that still will by magnitude will be so small that it will not interfere P1 in any sense. That is the trick of that. So don't think exactly you can null, okay, it is very difficult. थोड़ा टेम्परेचर चेंज हुआ कि ये सबकी वैल्यू अलग अलग चेंज होती है, so they will not actually null it, but very close to null. So we said it does not affect you very much. Is that clear? So at the end of the day, ये आपका आउटपुट आया सब. I have made a choice of 2.5 PF for a FIM of 60 and Z1 of 10 GBW. This was my choice. As a designer, you have a choice to choose this. Is that clear? This 60 degree is my making. You choose 70, you choose 50, 55, your choice. You choose 10 times, 50 times. I have already given you a table how much what values it will shift. The DC gain is 9225 at 25 microamps of current. Expected was only 4000, okay, or above 4000. So we have already achieved that. Bandwidth, because of this larger gain, how much is the bandwidth came? 4 kilohertz. So very low bandwidth op-amp we have received, okay, not even megahertz. The reason is our gain bandwidth itself which was very small, okay, 6 megahertz, okay. Is that clear? If your gain bandwidth point is here, so the slope if you put it by so much gain, P1 will be very small anyway, okay. So then adjust that value so that your bandwidths are higher, okay. Further reduction is CC because you are improving P2, so you actually went more left side, P1 became even lower. So that CC can then help you by RZ so that you can still maintain little higher P1 value, okay. V out maximum is 2.3, expected was 2, V out minimum expected was -2, so you are minus 2.27. P dissipation 0.725, you are expecting less than 2.5, I am 1/3 of it or almost 1/3 of it. Channel length used by me is 0.8 and the W by L size I got is 1 and 2 are 3, 3 and 4 are 12, 5 is 8, 6 is 92, 7 is 30. 8 we have not calculated because I do not know for those value of how much RZ I need, because for a given P2 I will have to do that, okay. For a given CC find P2 and then get that value of this. So I right now put it question mark. 9 is 4, 12 is 4. I also did not talk about 10 and 11. What are those values? How much VA, VB you want, that may decide their W by S drop across them, okay. And the bias resistor used in my analysis is 325 kilo ohms, okay. So do you agree that whatever specs given to me, I have achieved almost every one of them? Is that correct? Almost every one of them. So that means I have designed an op-amp for given specifications. Finally, this is what the circuit looks. आपको बोला ही मैंने ये VA dash, VA dash जो है जो यहाँ लगाना है, you can decide these values corresponding to adjust this value so that the transistor may remain in saturation or in non-saturation, whichever R you are looking for, and correspondingly create RZ there. We have calculated W by L here, 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 W by L here. So I am able to evaluate every size of a given transistor for given specification of my choice. Is that clear to you? Okay.
Sir, for CC also we need to put one MOS capacitor.
CC is a variable. CC is not given to me. Is that clear to you? CC I will make a choice from the phase margin I choose. Okay. So if
In circuit I need to put their MOS capacitor.
ये CC लगा हुआ है ना यहाँ पर.
वहाँ पर एक्चुअल में चिप पे इम्प्लीमेंट
नहीं हाँ, that will not be equal to CGD's values. It is much higher, not 2 puff higher बाबा, वो तो फेमटो में कितना भी पैरासिटिक लोगे तो फेमटोज में है, ये तो पफ में आ रहा है, you got it? So that value physically you will have to put. You have to create a mass capacitor right there. How do you keep a mass capacitor? अभी देखो mass capacitor कैसा बनता है, got it? सोर्स ड्रेन को कनेक्ट कर दो, ओके, और ग्राउंड भी कर दो, और नीचे से बायस लगाओ तो ये VGS, ये कैपेसिटेंस हो गया. So you actually create CC by a mass capacitor, okay. Please remember the only thing, this voltage is also very important because the CC will be function of this voltage. कितना capacitance इस oxide thickness है और किस size पे लिया जा रहा है, that will decide the, this should make an inversion and it should also in the size of CC you are looking for per unit area. So W by L you have to adjust for this value as well to get the CC value. And please, I am telling you, it is not small capacitor, it is very large capacitor, and much of the area in chip is actually taken by CCs. ट्रांजिस्टर इतना और कैपेसिटर इतना, ये सब सर्किट मिलके इससे छोटे होते हैं. That's the value, kind of values you get. Is that clear to you? So please don't think, another capacitors you can make, but that is very difficult because if you have a technology which is called poly oxide, sorry, yeah, poly, yeah, oxide, or ये भी poly, it's called POP. Okay. If you have more than one layer of oxides available and double poly process, then you can create poly oxide poly, okay, or at times metal oxide poly, okay. So don't use substrate, use the upper layer of poly value and use another capacitor on that. The advantage there is these are independent of biases. Is that clear? These are like a standard capacitors. Additional mask, paisa. But if the technology has that, then no additional mask because that process is anyway sitting there. Okay. Additionally, if you do anything, additional money. कल पूछ रहे थे ना, additional money कोई नहीं देना चाहता. देते हो तो फिर कर ही दें. So generally in most capacitors in RF circuits are always of this kind because their LCO is so strictly see I need, no variations I tolerate, okay. So I will use double poly process so that I can get this capacitors of my choice, okay. So please take it that it's not that this technology, but RF technology is not same as analog technology, okay. उसका अलग है, इसका अलग है. पर यदि आपके पास मिक्स सिग्नल टेक्नोलॉजी में ये सब अवेलेबल है, do it, definitely do it, okay. So next time when we come, we'll start of ICMR again, verify those issues. Today is already up.